All right, so we're gonna start off with some review. Here's P threads plus mutex recap. We've already done the recap today, so we're gonna just blast through this. Running the program. When you run the program, you can actually reduce thread count. So max threads supported by your system is 112. Shared variable value. This is showing how you can go through and have these different threads that are going and changing a variable inside the system in a known or unknown way. So this is the unknown way. We introduce mutex locks. So now that variable can be updated in a known manner. And so now we can run this and it actually gets updated the way we want it to be updated. Okay, so mutex locks allow us to control which thread is going to access which variable, or only one thread is going to access a variable at a given time. All right, so we're going to talk a little bit more about implementing that lock. How does the mutex lock actually work? Because a mutex lock is a special structure that goes deeper than just a normal variable. So mutex locks actually have to be supported inside the instruction set architecture, right? So there are special ISA value or ISA instructions that are introduced for locking variables. All right, so what does it mean? Why do we need it? Let's say that we have two threads. They're both pointing to some data that's in a memory. They both want to update it. We only want them to update it if it is available, right? So both threads might read R5, update it to 1, then write 1 in the same order. Correct value should be 2, but actually comes out 1 if we don't implement locking correctly. All right, so risk 5, how do we do this? Risk 5 introduces these instructions, okay? And these instructions are specific to multi-threaded mutex locks. The same way we did lab number 1, the same way we did lab number 2. We now have a problem where we need to execute the microcode associated with these instructions to go out and check the cache to see if locks have been implemented. We can do that. We just have to understand these instructions. If that's beyond the scope of this course, just know that that's how it's done. We introduce new instructions that go out and actually allow us to check a lock on a variable. If the variable is able to be locked, there's an instruction that locks it. So this is a coordination between the CPU and the cache. So now part of the cache overhead needs to be 1 bit to indicate locking. Does that make sense to everybody? Do all those words make sense? Cache overhead? Yeah? You can do this. You just have to sit down and think about it for long enough. We're not going to do it in class though. All right, on the green sheet, this is what it says, how it's actually done. Again, we're not going to go through it, but if the lock is set, data cannot be read or written. That's the gist of it. That's what it gets down to. And here's the pseudocode for actually how it works. We're going to check the CSR based on some registered value or based on some immediate value, and we can either AND it or just store the value of it. Does that make sense? We're going to check the locks. That's all it's doing. All right, thread level parallelism. So we want to be able to run threads. So we need hardware, multi-threading, and we need multi-processor. Meaning that inside a single CPU, we need to be able to switch out threads. And then inside a system that has multiple CPUs, we need to be able to identify and switch out threads and provide communication between those two CPUs for things such as locking. All right, how can we guarantee no dependencies between instructions in a pipeline? How are we doing this? How did we do this in lab 2? When you were in lab 2, what were some of the tricks that we used in order to identify problems? And what were the problems called?
Checked instructions that were like further along in the pipeline to see if the current instruction is using any of the registers or the memory that of the previously executed instructions I've already used.
Perfect. And if they were, we had two things that we implemented to try to solve it.
We would either stall out the pipeline, just wait for it to finish, or we would forward the data directly into the instruction.
Perfect. So we're either gonna stall or we're gonna forward. Those were the two tools that have been introduced to you up until now. Now I'm gonna introduce a third tool that you can use. One way is to interleave execution of instructions from different program threads on the same pipeline. We have a 5-stage pipeline. But for forwarding, how far ahead did you have to look? 3. Because we have the 5 stages, fetch and decode, they always would execute no matter what. And so we have the other 3 stages that we could look forward into time. But we only could really forward from 2 because by the time you got to memory or right back, it was always already coming back. So yeah, what we can do though is instead of saying, okay, this is the structure we're currently using, where we're stalling, we're gonna wait, and the bubbles float downstream. So this creates a problem. Instead of doing that, let's actually change up the game. We're gonna interleave different threads. So here's instruction 1 from thread 1. Here's instruction 1 from thread 2. Here's instruction 3, or instruction 1 from thread 3. Instruction 1 from thread 4. Instruction 2 from thread 1. Does that make sense? So now, if we look at the state of execution, we have fetch, decode, execute, memory, write back. Write back for thread 1 is concluding when we are starting decode of instruction 2. So if we do this in this manner, we can completely eliminate all forwarding. We're no longer going to forward. Because the whole idea of forwarding was let's avoid waiting those 3 clock cycles and instead move the data where it needs to move. Now we're taking a different approach. Instead of saying let's move the data forward, let's say let's just wait to run that second instruction until we know the prior instruction has completed the pipeline. Well, what do we do in those 3 clock periods in between? Let's do other work. Does that make sense? This is a multi-core process. So you have one pipeline, but in that one pipeline, there are 4 different threads that are simultaneously executing. Does that make sense? So that's why you usually have a 4-core processor. What problems does this create?
Don't you create more dependencies if you use the same register like in R5?
Yes, you're getting it, exactly. Your register space. Currently in our pipeline, we map to 1 register space, but that's no longer gonna work. So how can we solve that? In computer architecture, we are presented with the problem. The first thing we always do to solve that problem is add more hardware. You guys are getting it. Outstanding. Okay. We have 4 threads that are executing simultaneously. How many sets of registers do we need? That's it. We're going to add more hardware. We're going to replicate the register space. What about the PC? Or PCs. Can we do this? Yeah, we just replicate the PCs, throw in another mux, and now we need another piece of hardware, is the thread counter. Let's track which thread it is. We tie the thread counter to all the muxes that we created. And it just switches the muxes through the different general purpose registers and the PCs. All right, so if we have a cache miss, this is what happens. Cache miss is much more costly, right? We can't get around that. So there is still a situation where we might need to stall. But do we have as many bubbles floating through the pipeline here? Not nearly as many.
Instead of stalling, couldn't we just run the code for other threads in the meantime?
We could, but that's called a context switch. And we have to change out our PC and our general purpose registers. So that's costly. So if you're only stalling for a couple, go ahead and stall. But if you stall for too many, context switch. What is the definition of too many? That's up to the operating system. Okay. This has much less yellow though than this one does. The yellow are all the bubbles floating through the pipeline. So by going to a multi-core system, even though we're stalling, it's not impacting performance as much because we're only stalling on one of the threads. The other three threads can keep running. So what does that mean for our stall controller? It's going to need to be a little bit more complicated, but not much because it's just going to stall by checking the addresses of only those things that are on the same thread. Does that make sense?
Would the cache need to keep track of like which thread got?
Outstanding question. How about the cache? How would this work with a single L1 cache? Let's say we don't replicate our cache. How could we make this work?
I think different cores have different L1 level caches, but the other level is shared. So like if one core is running one thread, they might deposit their stuff in one cache and they wouldn't like see. But if it's something shared, it would go to maybe another shared memory.
Perfect. So there's two ways we can handle this. First way is we segment up L1 and say, you all still have L1 cache, but it's much smaller. Or we make L1 bigger and then give each one a part of it. But let's say that we don't. Let's say that we keep L1 shared between all of these. What would that imply as a restriction to the threads that are running on them?
You have to introduce more cache overhead to keep track of the thread.
You can introduce more cache overhead and keep track of the thread. You'd introduce a thread ID into the cache. There's one more solution that nobody said yet. Limit the address space? No. How many threads does a process run? How many?
Depends on the process, or depends on the OS.
Depends on the threads, it depends on the process. If I go again to this computer that's running currently, and let's go to Task Manager and look at this. Task Manager, we're gonna go to our performance. Currently, I have 210 processes running. I have 2,500 threads. On average, how many threads per process? About 10, right? So every process that's running has about 10 threads. So the other thing we could do is say all threads that are running on this core must belong to the same process, because then they'll exist in the same virtual memory space. Does that make sense?
So you have process IDs as well as thread IDs.
Yes. So then you can restrict it and say this core is owned by this process. Use all those. That's usually done more in high performance computing. Sharing of the cache is more done on a general purpose CPU. All those are solutions. They all work, and there's different times that you would want to apply them dependent on the requirements of your computer architecture. Does that make sense? So what does it mean to have a hardware thread? Each thread has its own PC. Each thread has its own general purpose registers. So here's what our pipeline now looks like. We have to add some hardware, but that's not too much hardware to add. Does that make sense? Everybody with me? We have a MUX. We have a thread selector, a thread counter. It has its own pipeline registers, just like all other control signals. And now we have multiple copies of the PC and the general purpose registers. The rest of the pipeline stays the same. This is a multi-core processor. So we can have multiple CPUs, physical chips on the motherboard. Or we can have a single chip with a single pipeline and we divide it. This is a good solution. It's not quite as powerful as giving it 4 unique processors, but it does a lot to solve a lot of our problems. It actually simplifies the way we have to do things because we're going to implement this instead of forwarding. So it simplifies our CPU design significantly, but it complicates it in other ways. All right. All right, what does it mean to have a hardware thread? So we have to store the user state. Each thread has its own PC. Each thread has its own general purpose registers. But we also have a system state associated with these. Each thread has its own virtual memory page table base register. Each thread has its own page table base register. Each thread has its own exception handling register. Okay, so these things are going to be created when we create the threads, so they can go to different places. Now, this says each thread, depending on how the operating system actually runs it, you could have a process have its own virtual memory page table. Does that make sense? In other words, multi-threading replication of individual content, but it has a shared pipeline. The vast majority of the hardware is shared, but we replicate its states, PC, the general purpose registers. In a multiprocessor, the control path and the data path will also be replicated because our stall controller now does not go to the entire pipeline, right? Stall controller, if you're stalling, you want to allow, if you're stalling on thread 1, you want to let threads 2, 3, and 4 continue forward. So that creates a little bit more complexity in the CPU design. Not much though. Potential performance increase issues. Increased conflicts in the cache. Exactly what we were talking about earlier. Now the cache, either you make the cache bigger or you have a smaller cache that's now being shared by multiple threads. So you have to have a way to resolve that. Increased conflicts in the TLBs. Increased conflicts in the TLB because, again, you have multiple things that are using that one shared resource. Branch predictor entry aliasing. If we have 4 threads and they are all in different virtual memory spaces, we could have branch predictor aliasing, and this actually can cause a lot of problems. And so this is one of the big things that has allowed a lot of viruses to get into the world, because branch predictors are very hard to nail down. Does that make sense? How thread scheduling, fine-grained multi-threading. Context switch among threads every cycle. That's what we're talking here. Every cycle, it's switching through those 4 threads. But all of those 4 thread states are stored in hardware. But then we could have a coarse-grained multi-threading. Context switching among threads every few cycles. So you might let the processor go for a while and then you switch it out. That's what you're doing in lab 1, the current lab part 1. When we already talked about these reasons why you might want to switch out something. We were saying there might be interrupts. Here's some more reasons. A functional unit data hazard. If you have a data hazard, instead of stalling, you might have a queue of threads that are still in hardware that are waiting to go into the CPU. Does that make sense? And so that lowers the overhead to bring those in and switch them out. So you might have just a couple of threads that are waiting in the wings. And if one starts to stall, the hardware immediately switches it out without asking permission from the OS, because it has already allocated a thread to wait. That might happen for functional data units, L1, L2 miss. So these are some examples of how we can create computer architectures to do fine-grained and coarse-grained multi-threading. This would be at the hardware level. Now we can do a context switch overhead, and this is where we're actually going to involve the operating system in order to switch between them. All right? Everybody with me? So we have a lot of options. These options are only limited by your imagination and the cost to produce the silicon. Right? Go and take advanced computer architectures if you want to learn more about all this stuff. This is where it really starts to get interesting. All right, going on from here. What are the problems with multiprocessors? We're going to start to scale things up. Have we scaled anything up before in this class? And we always run into some type of limit. Does anybody remember the rule or the law that governs the amount of speed up that we can achieve by parallelism. Amdahl's law, that's right. So it's gonna apply here also. Performance, communication and parallelism, scheduling, and then programming. We have to think about coherence amongst the different processors and how that's gonna impact us. So let's first talk about scaling. So suppose a program solves problem P in time T, example, folding a protein in 1 hour. This can be called a strong scaling because you can run the problem faster, fold the protein in 1 minute. In order to do this, you can distribute it to a lot of machines because there's no overlap in this. That makes sense. So you can segment the problem very clean and allocate that to a whole bunch of resources. So it has the strong potential for scaling. Challenge, Amdahl's law, we still have this. So even if you are taking thread folding and segmenting it up and distributing it to a whole bunch of things, you still at the end have to bring that back together and put it into one coherent answer. So there's still that non-parallel part that cannot be optimized. And that's what we see here. All right, weak scaling. Suppose a program solves a problem P in time T, folding the protein. Weak scaling, we can run a larger problem or more. Fold bigger proteins or multiple proteins. Gustafson's law assumes data set scaling. So on this one, if we're folding multiple proteins, all of them can be applied. So all of them are still going to have that serial and the parallel portion, but we can do all of these in a multiprocessor sense at the same time. So that makes sense. So we can take the problem, and even though it might not lend itself, we can distribute it because they are completely different, completely independent optimization problems. There's weak connection between them. We don't have to put them all back together at the end because we're going to do multiple at the same time. So let me say this differently. Let's say that you have a nested for loop. The first for loop says you're going to fold 100 proteins. The nested for loop says that you're going to break that protein up into so many segments. It's one way to do it. The other way you can look at it is to change that nesting. You can say the for loop, I'm going to break it up, and then the internal for loop and say that you're going to do all the proteins. So it depends on how you look at the problem. If you're going to take one problem and break it up into small things, or if you're going to take that same problem and look at it as multiple small problems. All right, so first we have to understand our problem. Then we can tell if it's a good problem for parallelism. In order to do this, we need to have it on multiple processors. So do N processors mean a speed up of N? Everybody should know this. Does it? No, not at all. We know that speed up is based on this ratio of the original plus the new. And then we can say that the runtime is going to be the instructions total times the CPI times the clock period. And ideally, if we have more instructions, we can get a speed up, but we know it's not feasible because we have all these overheads. We have all these limitations that are put upon it. This is the same equation that we were running when we were talking about bus communications, right? Parallelism limits the number of instructions that can run in parallel because there's always that serial portion. All right, so suppose we have a CPI of 0.4, we have a remote request rate, we have a remote cost rate, and then we're going to say our clock is 3 gigahertz. Have we done something similar to this before in this class? CPI new is going to be the CPI of the original plus the remote request rate times the remote request cost. This is the same equation that we were using for the cache miss time or the average cache access time. So if we think about this, as we thought about caches, where we have a system that either is going to work or not, we now can say the same thing. We have the original, we have the penalty. We have the penalty, and then we have the speed up rate. And applying that, we can find the new rate. So the speed up given n processors, we can see that we need 7 processors just to break even. Given this cost equation, which is the same cost equation that we were using for our cache structure. Does that make sense? So, have we seen this before? Yes. So suppose f is equal to 0.9, n is equal to 1,000, speed up of 10 limited by the serial portion. That is the theoretical limit. This is the absolute fastest that we can ever run it. Because the serial portion is going to start to dominate. And it doesn't matter how fast we speed up the parallel portion. As that approaches infinity, the number of processors approaches infinity, the parallel portion approaches 0. Serial portion is still the serial portion. Doesn't matter. It's still that same value. And so that's the theoretical limit of how much we can speed up an application when using parallel computing. All right, scheduling. This is lab number 5. You're going through it right now. We're not doing the longest time, remaining time first, right? You're doing this semester, we're doing FIFO and round robin. So there's another algorithm that's called longest remaining time first. And I think, did we leave some of that stuff up on the website, or did I have the TAs take it all down? Still there?
So there.
Okay, still there so you can read through it. Basically, they look at the queue and say, who's been waiting the longest? Right? And they go and access that individual, that thread. These are very, 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 very simple policies. Complex policies. Locality. Place threads close to their data. This starts to talk about if we have a multi-core processor and the thread that's running on there is from a process, we might want to put other process threads on that same core because we know that in the L1 cache is going to be the data that both those threads might use. Does that make sense? So now you need to have an understanding of the hardware to optimize thread scheduling. Because if there's no difference to the operating system, it's just going to throw threads random. But if you inform the operating system more about hardware, it can make better decisions as to where to schedule. Quality of service, cache affinity. These are different things that you're going to talk about in advanced computer architectures. But know that FIFO and round robin are not efficient. They're not good ways to schedule things. But this is to introduce you to the concept of thread scheduling. Everybody with me? Again, if you want to learn more about that, take the advanced computer architectures class. Programming multiprocessors. So we have shared memory and we have message passing. So shared memory, all threads on processors see the same address space. This is one technique of doing it. So in this, the virtual memory that you have is shared amongst all the threads of that process, right? And in this, you now have a very strong ability to quickly access data, no matter what core it's running on. What's the downside to this? What happens when you need to run the OS into that core? When you need to do a context switch to the OS? You have to invalidate that entire cache, and then you have to reload the cache from scratch when you context switch back. Same with any other process. Implicit communications by reading, writing memory. If processor X writes to address A, processor Y eventually sees the value at address A. This is what we were talking about last time. Let's see if this marker works. You have 2 cores. They each have L1. They each have L2. They each have a shared L3. L3, L2, L1, CPU, CPU. Data has to go here and eventually come back here. Does that make sense? So if you're sharing something, we have to optimize this data path to get data to move up and down. we now have to start to inform the cache that a change has been made. So that implies that we're gonna have to start having communication here. Does that make sense? We're gonna talk about that in the next slide deck. Message passing. Each processor has its own address space. Explicit communication via send and receive. Programming model, process plus interprocess communication. These are two different ways we can do it, two different ways of looking at things, right? So if you're going to do a shared memory space, everybody gets to see the same thing. If you're going to do a message passing, that means everybody has their own space and you're going to pass messages back and forth between it in order to communicate. These are different structures that we can implement and optimize depending on what our goal is. Modern multiprocessor, the M2 has between 10 and 12 CPU cores. GPU has 19 cores. It's in a laptop. It costs about $2,300. Intel 14th generation i9 has 24 cores and 32 threads. What does this mean if we have 24 cores and 32 threads?
I think Intel has like efficiency cores that don't multi-thread.
There are some that do multi-threads, but if they have 24 cores, but they can hold 32 threads, that means some threads are sitting there waiting in the wings. So we're allocating threads to a piece of hardware, and then it can do coarse context switching or coarse thread switching to pull those into an active core without having to consult the operating system. Does that make sense? So we can allocate threads to the hardware, but those hardware might not instantly get a core. So this is Diego. He's one of the other professors that teaches the course. So his laptop has a 12th gen i7. It has 10 cores with 12 logical processors. So if we have 12 logical processors, what does that mean? This is what we actually see when we do Control-Alt-Delete and look at it through the OS. So it's presenting this many cores. So this one, 10 cores, that means there are 10 cores. Some of those are multi-threaded, but not all of them. All right? 3, because he got it with work. So there are tons of different options for how these different structures are made, and there's tons of different cost across them based on their optimization.